Another extremely important concept that involves line integrals is the concept of flux. It's extremely important in many dynamic situations where we're working with vector field. Flux is a very important application that line integrals come into play with. Flux is the measure of the components of a vector field F that lie orthogonal or normal to all points on the curve C, where C is a smooth curve that does not intersect itself, meaning C is just a simple curve. C also may or may not be closed. And because we're now looking for vector components that are normal to C, our line integral will still involve a dot product, but this time we will be dotting the force vector with the normal unit vector. We need to define the unit normal vector n at a point P of the curve C. Now, since C lies in the xy plane, my unit tangent vector t also lies in the plane of C. The z component will be 0 because we're in the xy plane, so we're going to let my unit tangent vector be given by the components t sub x, t sub y, and 0. A vector of unit length 1 that is normal to the xy plane is given by k is equal to the vector with components 0, 0, 1. This is a unit vector in the z direction. Now, our unit normal vector n in the xy plane will be orthogonal to both the tangent vector and to my k vector. We can use my unit tangent vector and my normal vector k to determine n through the use of cross products between t and k. In other words, my unit normal vector to the curve C is given by the cross product of t and k. If C is a closed curve with a counterclockwise orientation, the unit normal vector points outward along the curve. If C is not a closed curve, the unit normal vector points to the right as the curve is traversed in the forward direction. So the first thing I need to do is figure out what my unit normal vector is using a cross product. I set up my cross product where my unit normal vector is given by the cross product of the vectors t and k. This is the determinant of a 3 by 3 matrix that has the first row populated with I hat, j hat, k hat, the second row populated by t sub x, t sub y, and 0, and the third row populated by 0, 0, 1. This gives me a determinant that's equal to t sub y in the I hat direction minus t sub x in the j hat direction. Keeping in mind that t is given by r prime of t over the magnitude of r prime of t, t is equal to a vector with components x prime of t, y prime of t, and 0 over the magnitude of r prime of t in 3 dimensions. So that my unit normal vector, specified by t sub y I hat minus t sub x j hat, is equal to y prime of t over the magnitude of r prime of t in the I hat direction, minus x prime of t over r prime of t in the j hat direction, is equal to the vector with components y prime of t and negative x prime of t over the magnitude of r prime of t. This means that my line integral over C of f dotted with n ds becomes the ordinary integral from a to b of f dotted with a vector with components y prime of t and negative x prime of t divided by the magnitude of r prime of t times the magnitude of r prime of t dt. But you'll notice that the magnitude of r prime of t cancels out, so that my integral becomes the integral from a to b of f times y prime of t minus g times x prime of t dt, where f and g are the components of my force vector f. And another way of writing this is the line integral over c of f dotted with n ds is equal to the line integral over c of f dy minus g dx. So for flux, we let f be the vector with components f and g, and this is a continuous vector field on a region R of R2. We're going to let c equal r of t, given by the vector with components x of t, y of t, and for a is less than or equal to t, which is less than or equal to b. This is a smooth oriented curve in R that does not intersect itself. The flux of the vector across C is given by the line integral over C of f dot n ds, which is equal to the ordinary integral from a to b of f y prime of t minus g x prime of t dt, where n is equal to the cross product of t and k, and it gives me the unit normal vector, normal to my curve C, and t is the unit tangent vector consistent with the orientation of my curve. If C is a closed curve in the counterclockwise orientation, n is the outward normal vector, and the flux integral gives the outward flux across C. So let's work an example. I want to consider the vector field and closed oriented curve C and make a conjecture about whether the outward flux of F on C is positive, negative, or zero. Then I want to compute the flux for the vector field and the curve C. My force field is given by the vector with components x, y, divided by the quantity x squared plus y squared to the 1/2 power, and C is the boundary of a square that has vertices at plus or minus 2 and plus or minus 2. In the sketch of the vector field that you see here, you will notice that all of my vectors point outward away from the origin in all directions of my coordinate system, and I'm bounded by my square with side lengths 4 in each direction. By observation, I notice that the vector field points outward at all points, so I'm expecting my flux to be positive on this particular vector field. The line integral over C of f dot n ds is equal to the line integral over C of f times y prime minus g times x prime, and I am expecting this to be greater than 0. Now I need to recognize that with my square boundary here, I actually have 4 paths that I need to consider, but I have to think about direction. And by convention, I take my orientation to be counterclockwise for the positive direction. This means that I'm going to have one path length that I call R1, which I'll take to be the right side of my square. My path length R2 will be the top of my square. My path length R3 will be the left side of my square, and the path length R4 will be the bottom of my square. Notice that I'm choosing to orient it so that the vectors always point counterclockwise around the perimeter of this square. R sub 1 of t is given by vector components 2 and negative 2 plus 4t, and R sub 1 prime of t is 0, 4. Fy prime minus gx prime is equal to 2 times 4 minus 0, or 8. My second path, R sub 2 of t, is given by a vector with components 2, minus 4t, and 2, and R sub 2 prime of t is given by the vector with components negative 4, 0. Fy prime minus gx prime is equal to 0 minus the product of 2 times negative 4, which gives me 8. R sub 3 is the vector with components negative 2 and 2 minus 4t. R sub 3 prime is the vector with components 0, negative 4. Fy prime minus gx prime gives me 8 again. R sub 4 of t is the vector with components negative 2 plus 4t and minus 2, and R sub 4 prime of t is the vector with components 4, 0. Fy prime minus gx prime again gives me 8. So now I need to set up my 4 integrals. My line integral over C of f dot n ds is equal to the integral from 0 to 1 of 8 over the square root of 8 minus 16t plus 16t squared dt, plus the integral from 0 to 1 of 8 over the square root of 8 minus 16t plus 16t squared dt, plus the integral from 0 to 1 of 8 over 8 minus 16t plus 16t squared dt, plus the integral from 0 to 1 of 8 over the square root of 8 minus 16t plus 16t squared dt. These integrands are all the same, so that my integral simplifies to the integral from 0 to 1 of 32 over the square root of 8 minus 16t plus 16t squared dt. This gives me 8 times the natural log of 2 square root of 2 plus 3, which is approximately 14.1. Now you get to try it. Pause the video and make a conjecture about whether the outward flux of F on C is positive, negative, or 0. Then compute the flux for the vector field and curve C. When you are ready, restart the video to check your understanding. Your vector field is given by a vector with components y minus x, and your curve C is given by r of t is equal to the vector with components 2 cosine t, 2 sine t, where 0 is less than or equal to t, which is less than or equal to 2 pi. My diagram of my flux field is given with the circle superimposed in the xy plane. In order to solve this, I need to first make my conjecture. I observe my vector field and my region C. I see that my vectors point inward in Q2 and Q4 and appear to be larger than the vectors that point outward in Q1 and Q3. This means that the magnitude of the inward pointing vectors is going to be overall greater in that region than the outward pointing vectors. This tells me that my flux should be negative. So using r of t given by the vector with components 2 cosine t, 2 sine t, r prime of t gives me the vector with components negative 2 sine t and 2 cosine t. F y prime minus gx prime gives me the quantity 2 sine t minus 2 cosine t times 2 cosine t minus 2 cosine t times negative 2 sine t. This gives me negative 4 times the quantity cosine squared t minus 2 sine t cosine t, so that my line integral over C of f dotted with n ds is equal to negative 4 times the integral from 0 to 2 pi of the quantity cosine squared t minus 2 sine t cosine t dt. I can integrate this term by term. This gives me negative 4 times the quantity t over 2 plus sine of 2t over 4 plus cosine of 2t over 2 evaluated from 0 to 2 pi. This gives me negative 4 times the quantity pi plus 1/2 minus 1/2, or negative 4 pi, so that I did find that my flux was in fact negative for this particular oriented curve. Be sure and let me know if you have any questions about line integrals and working with flux.